If you recall, we were discussing how the distillation column, that is the crude distillation column, separates out all the fractions of the crude oil, particularly the light fractions, the naphtha, the kerosene, diesel, and if required, I mean, they're called by different names. In this particular diagram, as you can see, this is what I explained earlier. So the crude comes here. So this is a representation of the cold preheat train. Then it goes into a desalter. From the desalter, actually, the crude again gets preheated. Here, of course, we don't have a pre-flash. So there's one train only. In fact, in good old days, units were designed like that. Actually, pre-flash concept was not known. And so basically after that, at about 250 to 270, the crude enters the furnace and gets heated up in the range of between 360 to 370, 372. We don't go beyond that, otherwise it cracks. And the amount of heat that we give in order to vaporize the crude is only to the extent that none of the long residue or atmospheric residue gets evaporated. So basically, this is a flash where actually the liquid drops out, the heavy liquid, and the light fractions all the way from fuel gas to LPG to light naphtha, heavy naphtha, kerosene, diesel, everything comes up to the top. And then I told you about how this crude column is different as compared to the columns that you have studied or the mass transfer courses that you have taken in your undergraduate class. In order to explain the whole thing, I said that the crude distillation column can be actually divided into various zones. One is the bottom zone, then the flash zone, the wash zone, and then the product zones. And the vapor comes up to the top, it condenses and then collects in the overhead vessel along with the water. The steam also condenses, the steam that we put at the bottom, and also the steam that we put along with the side strippers. So that comes down and we collect the water from the top. And then actually, in order to get into the details of each of these sections in the crude column, at the bottom is the bottom stripping zone. So the crude oil comes here and it flashes and the residue drops off. That is the atmospheric residue or what we call as long residue. And that gets stripped by steam. This is the kind of a ratio that we use, 18 to 24 kg per meter cube. And the idea here is that the steam actually strips all the dissolved hydrocarbons in this residue so that none of the diesel components go in. So, and that actually helps us to increase the IVP of the top crude. This is also called as a top crude. Then as the vapors go up, so this is the flash zone where actually the crude comes and flashes, where the vapor goes to the top and the liquid comes to the bottom. And there is actually no trace here, but if you remember, I mentioned that a lot of licensors of this technology, they actually use all kinds of devices for very effective separation between vapor and liquid, because this comes at a pretty high velocity. Okay. So people use vortexes or vortex separators, etc. And in many columns, actually, it is crude oil has a tangential entry rather than a straight entry. The flash zone temperature is related to the crude oil temperature, roughly in the range of 350 to 370 in that range. But the amount of heat that we provide in crude oil also actually is slightly more as compared to the sum total of all the products, because we also create what is called as an overflash or slop oil. And that overflash, so this is the function of the wash zone. This section is just above the flash zone, where the liquid actually, there's a vapor liquid contacting in order to actually ensure that no entrained droplets of the long residue travel up to the top. So the liquid actually does a wash, in other words, it does a kind of a washing function. And so we actually produce some extra liquid, some extra vapor actually by preheating the crude by another 2 or 3 degrees, so that we create this liquid which we can use for washing in this section. And then above the wash zone, we have several product zones. And this is actually what I told you, that when the crude vapors come up, the heaviest the heaviest cut we withdraw first, which is the gas oil. This is the heavy gas oil, and then the next cut is the diesel, and the next after that is the kerosene, and then if in some columns you might even have a heavy naphtha withdrawal. But generally, the kerosene is more or less the last, or basically the first withdrawal from the top. And each of these sections actually has a pump around. And if you remember, I had explained the function of the pump around. It is actually more or less like a reflux that you have at the top of the column. The reflux we provide at the top of the column, if you remember what was taught in your master's course, in your undergraduate course, is that how the reflux helps us to give a better fractionation is that the less volatile components which are actually trying to come to the top, they are actually condensed by the reflux, which is actually rich in more volatile components. So basically, there is an exchange between the vapor and the liquid with respect to the components. So basically, from the reflux, we actually condense the more volatile, less volatile components, and in turn, actually, we vaporize more volatile components, which actually add to the vapor. And the vapor, when it travels up, it actually condenses less volatile components. So here also, it is exactly the same. The liquid, the same product which is withdrawn is actually circulated back after cooling, and that helps to actually condense only the gas oil part in this section. And then above that, we still have everything else, including diesel. And so this pump around condenses the diesel part. And rest actually, if you remember, I had explained that each of these sections could be having something like 8 to 10 actual trays, and there are side draws with strippers, and we'll talk about the strippers later. Okay. And the pump around I've already explained. Actually, yesterday I drew a picture which perhaps it would be easy for you to understand. So if you remember this column, the structure of the column, more importantly, this actually, where we are withdrawing the products. And the way actually this column, it can be represented thermodynamically is that you got crude coming from the furnace. So we see from bottom upwards, the crude coming from the furnace, and it flashes, right? And so basically the liquid withdraws and you got steam stripping. Now the vapor from the crude, which now contains everything other than atmospheric residue, that travels to the top, and the heavy gas oil fraction that we are withdrawing, part of it actually is cooled and taken to the top. So this actually acts like a reflux. And the amount of heat withdrawal that we do here, obviously this heat is actually, taken into the crude preheat train. And in this case, it might be actually in the hot preheat train. So this cools and condenses all the vapors, the diesel fraction, which is trying to go up. So all the diesel kind components, diesel range components going here get condensed, and they actually travel down, and that's where we withdraw it. Beyond this particular column, you have basically now vapor, which is everything else other than these two fractions, heavy gas oil. And it has everything, including diesel. So when it goes up, you have another pump around. So the diesel is actually cooled, and we take it back again on the top, which condenses all the diesel part of the hydrocarbons. And then what goes up to the kerosene section is the fuel gas plus LPG plus naphtha plus kerosene. And the same thing is done there at the top as well, where we take the kerosene side drop and then cool it and condense the vapors. So this is actually, I thought I'll draw this in order to help you to understand and actually relate to what you learned in your undergraduate classes. I mean, it's actually, I mean, this column that you see here is nothing but several columns, one above the other. So I hope now you will be you have a better picture of how these columns really operate thermodynamically. Now, when I say thermodynamically means actually trying to separate between the components based on their volatility in terms of their boiling points. And if you recall, we said that this separation, let's say, between diesel and gas oil and diesel and kerosene, etc., can be represented again on this crude TBP diagram. This is temperature versus volume, and this is the TBP curve of the crude. And so this is the, let's say, the the light fraction and the heavy fraction. These are the cut points. Okay, so this is actually, let's say, 20% volume, 15% volume, etc. And basically, the boiling range of this particular fraction is from here to here, and from there to there. So basically, if you travel along the TBP curve, the light fraction boils from here to this temperature, and the heavy fraction boils from this temperature to this temperature. And basically, the draw temperature of the temperature at which we draw the products roughly matches with these temperatures, which are actually shown here. So it actually matches with the mean average boiling point, what we discussed in earlier classes. So this is the temperature at which you draw the light fraction. This is the temperature at which you draw the heavy fraction. And but the real life, cases are not like that. We don't have a very clear cut like we have shown here. Basically, when you withdraw, let's say this is light naphtha, this is heavy naphtha, kerosene, gas oil, you will see that actually some of the light portion of kerosene goes along with the naphtha as well. And some of the heavy portion of naphtha goes along with the kerosene, because it is something very similar when we actually, let's say, I gave you an example, when you distill benzene and toluene. Some toluene will go to the top and some benzene will come to the bottom. It's not that and that's how we design these columns. If you remember your McCabe field diagram, so we say that we need 95% purity at the top and 95% purity of the heavy component at the bottom. So something similar we actually try to do here. We try to maximize the naphtha components in naphtha, and we try to maximize the kerosene component in kerosene. But nonetheless, some portions do actually go either way. And basically, if you take the kerosene fraction, therefore, and if you do a TBP of that, so you will find that it actually goes something like this. It actually, let's say, brackets the typical crude TBP curve. So this is the crude TBP curve. And the mean average boiling point will be exactly the same. So this is the cut point, let's say. This is actually at the temperature at which you withdraw the kerosene fraction from the crude column, of course, corrected to atmospheric pressure. And these are the endpoints. So this is like the percentage vapor recovery, percentage recovery that you see in a typical TBP diagram. From there, I actually explained the definition of gap and overlap. Please always remember these definitions. The gap can be explained by the top diagram, where this is the TBP curve of the crude, and this is the lighter fraction, and this is the heavier fraction. And if you remember that above the mean average boiling point, the ASTM, the TBP graph is always above the ASTM. And below the mean average boiling point, the TBP graph is, the TBP graph is always above the ASTM here. And below the mean average boiling point, the TBP graph is below the ASTM. So there's negative correction and there's a positive correction. So if those equations that we discussed. So you can see that if there's a very sharp cut, then actually there's a gap on the ASTM graph. So this gap is actually based on the IBP and the EP. While actually if suppose the fractionation is not that perfect, and it is always the case that the fractionation is not that perfect, then the light fraction ASTM and the heavy fraction ASTM, that is how we define the overlap. That is the endpoint of the light fraction minus the IBP of the heavy fraction. So this is kind of summarized in the next two slides. That is the ASTM gap is defined as the difference between the 5% boiling point of the heavy fraction and 95% boiling point of the previous fraction. That is the lighter fraction. So you have 5% boiling point of the heavy fraction minus the 5%, 95% boiling point of the light fraction. So that is how you define the ASTM gap. The ASTM overlap is actually that is basically TBP overlap. That is actually defined as just a simple difference between the final boiling point and the initial boiling point of successive fractions. That is the final boiling point of the light fraction and the initial boiling point of the heavy fraction. So going from there, then this is where we stopped last time, and going from there, this is actually a more detailed discussion on the strippers. So if you recall, the products were withdrawn, and they actually entered these strippers. The main function of the stripper in a crude distillation column is to actually remove any light material which might actually be dissolved or come along with that particular fraction. So if suppose some very, some very end portion of the naphtha comes along with the kerosene, so that will actually reduce the IBP. It will reduce the 10% point, and therefore actually it will actually reduce the increase the flash point. Sorry, reduce the flash point. So if you reduce the flash point, then actually that kerosene becomes dangerous to use, particularly in the cooking stoves that we use, and there's a possibility of explosion. So what we do is that in these strippers, this is typically containing about 4 to 6 theoretical plates, 4 to 6 actual trays. These are actually typically sieve trays, and we put steam at the bottom. The steam flow rate is same as we had before, about 12 to 18, slightly less as compared to what we had at the column bottom, around 12 to 18 kg per standard meter cube of the product at 15 degree. And this actually helps to increase the 5% distillation temperature of the distillate that we remove. So we actually don't try to put too much of steam, only the amount that is good enough to meet the flash point specifications. And if you recall, last time I mentioned that in some of the streams, we perhaps don't do any stripping at all, or actually we do stripping with a reboiler. So rather than actually putting a live steam, open steam here, we actually take this side distillate and put a reboiler and back. And this is done mostly for kerosene fractions because, and particularly if you're making jet fuel. So if you're making jet fuel, that water actually can get dissolved in the jet fuel at that temperature, and and at a lower temperature than at temperature at which you store ATF at ambient temperature, this dissolved water can actually come out as water droplets. And so these, I mean, this is not acceptable, particularly it doesn't meet, it actually, there's a test called water separometer index, and it doesn't meet that particular quality. And so actually it can create problem in the aircraft because that water can form ice and it can choke the nozzles in the jet engine. Coming on to the top of the column, it's a very traditional column, the way you have learned in your undergraduate classes. Basically, the vapor, whatever is not condensed, goes up to the top, and then it condenses. It could have one or more condensers, and it could even have a air cooler, what we call as a fin fan cooler. And after that, on the entire hydrocarbon that comes out to the top gets condensed to the extent possible. What doesn't get condensed actually goes out, and that is what we call as a fuel gas. So basically, everything containing this fuel gas is basically very sour fuel gas because it has H2S. Crude oil has pretty good quantity of dissolved H2S and C1, C2, that is methane, ethane. If it is the whatever is dissolved in the crude, so that gets out to the top. We actually condense everything here, right up to LPG components, because LPG is dissolved in this hydrocarbon stream, and we remove the water from this boot. This is called as a boot in the separator drum. It is just a kind of a cylindrical vessel which is welded on to the bottom of this. So it's a vertical vessel welded onto a horizontal vessel, so that we actually keep the water separate from the hydrocarbon. And then the hydrocarbon part of it is reflux back, same way that we had studied earlier, and part of it is actually withdrawn as a product. Now, this overhead liquid, we will come back to that in our subsequent slides. But this overhead liquid is actually containing little bit of fuel gas, of course, which is dissolved. Most of it actually comes out here, but also LPG and naphtha, that is both light and heavy naphtha, in case you don't withdraw heavy naphtha in the crude column. So just to read what is written here, yeah, one thing important that you need to remember is that the top temperature is maintained in such a way that actually it is at least 8 to 10 degree higher than the acid dew point. What we need by the acid dew point is actually the temperature at which water will condense here. Okay, so this water, if it condenses, it will dissolve H2S and it will corrode the top section of the column. So we try to maintain the overhead. So we try to maintain the reflux in such a way that it doesn't drop the top temperature to that extent that you might have water condensed at the top. And there are quite a few trays here actually after the last withdrawal. And as I said, in many cases, you actually try to recover the heat of this vapor into the crude in the cold preheat train. So actually, I'll show you a preheat train later, a kind of a actual example of a refinery. But generally, this may be true, may not be true, depending upon whether there is an opportunity for recovering this heat. So this is more in terms of heat integration and to reduce the heat requirement of the process. What we also do is that part of this water from this boot, this is called as a sour water because a lot of H2S get dissolved in this water. And so this is, just remember, it is called sour water. Yeah, it is written here. And so we actually reflux part of it back to the top to be able to help to condense the steam to the extent possible. And so this actually overhead liquid is withdrawn and it is actually sent to another column, which is called naphtha stabilizer. And we'll talk about the naphtha stabilizer. So here it is, the naphtha stabilizer. Actually, this particular stream is also called as wild naphtha. Why it is called as wild naphtha? Because actually, if you pour it out into a flask or a beaker, it will actually bubble. It will appear as if it is at its boiling point because the LPG starts boiling out. So that is why it is called as wild naphtha. But it is also actually the feed to the what is called as a naphtha stabilizer. This is a very important column in this crude unit, which actually helps you to separate out. The main function of the naphtha stabilizer is to distill off the LPG from the naphtha fraction. And both of them are very important streams in the refinery. LPG, as you already know, is liquefied petroleum gas, and this is the fuel that we use in our kitchen for cooking. And the naphtha is actually used making petrochemicals and also for making gasoline. So basically, the naphtha is a major stream in the refinery from which we actually make petrol or gasoline. The pressure in this column is such that we can use cooling water at the top. So as you know, we have LPG. So this is liquid LPG coming out at the top. So it is propane, butane. There is no propylene and butylene here because we are not because crude oil will not contain any olefins. But propane boiling point is pretty low. If we don't actually operate this column under high pressure, then we'll not be able to condense. Or if we have to condense, we have to use refrigeration here. So in order for us to use cooling water, these columns operate at about 10 to 11 kg per square centimeter. That means 10 to 11 to 12 atmosphere. So that we have LPG in the liquid form. And then we have naphtha coming out from the bottom. It's a traditional reboiler. In many cases, rather than putting steam, we use one of the hot streams from within the refinery to actually preheat to provide the reboiling duty. That means either we use the diesel pump around or the hot diesel going out from the crude column or something like that. Generally, the temperature profile here is something like 60, 75 to 80 degree at the top, and something like 170 at the bottom. So it's pretty hot at the bottom. So we need a pretty high, generally MP steam, medium pressure steam is used. And so we actually try to, what is the fractionation criteria here? That means what is the light key and the heavy key components. You must have actually, learned what is the definition of the light key and heavy key. So let me help you to recap what is the definition of the light key and heavy key. And the light key is a component which actually we do not want we want to minimize at the column bottom. And the heavy key is the component in the feed which we try to minimize at the column top. So if you look at the naphtha stabilizer, the separation is actually between C4 and C5. That means between butane and pentane, or in this case, if you have some isopentane, then it is between normal butane and isopentane. So the normal butane actually, some part of normal butane will actually go to the bottom, and some amount of isopentane will actually come with the LPG. So the number of theoretical stages that we provide and the reflux that we provide is actually same. You can actually design this column based on McCabe-Thiele diagram, no problem. And actually, Raoult's law is completely applicable here. So what we try to do is that we actually limit the C5 content in the LPG to less than 1%. Now, the reason why we try to limit the C5 content in the LPG to less than 1% is that when you use the cylinder at home, then there should not be any, non-vaporized hydrocarbon left in the cylinder, because that is actually a loss to you in terms of the money that you paid for that fuel. So we try to limit C5 content in the LPG to less than 1%. And that is checked by the vaporization. This is also called as a weathering test. So a lot of these terminologies I try to tell you, which are not actually written in the slides, but please remember them. This is called as a weathering test. What you do is, and this is something I have also done. So what you do is that you take a graduated 100 milliliter cylinder, and you open the tap of LPG in the refinery, and it actually fills out that measuring cylinder up to 100 ml. And then you put a thermometer in there, and you wait till the LPG vaporizes. And by the time it actually goes to something like 5 milliliter volume left, the temperature should not be more than 2 degree. It's shown in the thermometer, because as it vaporizes, it cools the liquid, because it takes the latent heat from the liquid itself. So actually the temperature drops. So LPG at ambient temperature, liquid LPG at ambient temperature, when the 95% vaporization happens, it will be 2 degrees. It is also called as a weathering test. This is a very good, very easy way to check whether we are meeting C5 content. But nowadays, of course, they actually analyze LPG in a GC, and a gas chromatograph, and that is how they actually determine the C5 content. Number of trays is, of course, around 40. Sometimes we provide even 50 trays. And the specification on the naphtha is in terms of the RVP. The more the butane content, the higher is the RVP. So we try to limit it between zero point 0.3 to zero point 0.7. So we don't allow, more than 1 to 2% normal butane in the naphtha. These are the broad product specifications. I think I've already discussed the vapor pressure of LPG. If you notice, I do not know whether you've seen the stampings on the cylinder at home, that red cylinder which the oil companies deliver. If you see the stamping on that, you will find that there is a design pressure and the vapor pressure also given of LPG. So the vapor pressure is this is the specification of LPG, just to actually make sure that you don't have a significant quantity of light components like ethane. So higher vapor pressure means lower vapor pressure means that you have some C2 content in that too. Sorry, the other way around. Higher vapor pressure means that you have C2 content in that as well, and of course the C5 content. So as far as the naphtha is concerned, which includes both light naphtha and heavy naphtha, we try to limit the final boiling point to 210. Sometimes it is 215 degrees Celsius, and the RVP, because otherwise you'll have a significant quantity of butane coming down, which is a loss, because otherwise C4 should actually go into the LPG component, into the LPG stream. So then in many refineries, actually this naphtha is then further distilled into a light naphtha and the heavy naphtha. So basically, we try to fractionate between the light naphtha and heavy naphtha at a certain cut point, which I'll actually discuss in more detail as we go to the secondary processing units in the next lecture. Jet fuel, I have already said, the major criteria here is the freezing point, minus 47 degrees Celsius, as well as the free water content, the smoke point, which is a representation of the aromatic content. The lower the aromatic content, higher is the smoke point, you already know, and the flash point. So jet fuel has many specifications. The aromatic content, the boiling range, final boiling point max is 300. We don't, I mean, we try to limit it below that so that it meets the freezing point specification. And flash point, of course, in order for it's a safety of handling jet fuel. As far as the kerosene is concerned, it's again the same thing like a jet fuel. Here, of course, we can afford to reduce the smoke point slightly and allow slightly more amount of aromatics. High-speed diesel, or in fact diesel that you get in the petrol station, the 90% volume recovery is 366 degrees, and the flash point specification in our country is 35. In fact, recently it got revised to 38 degrees Celsius. And that this has been an area of intensive discussion in the last 25 years, whether we should actually have a flash point. So you can see that the flash point of kerosene is also 35, diesel is also 35. So there's been a lot of discussion that maybe the flash point of diesel should be 60 degrees, 65 degrees. But but in order to maximize, the diesel content coming out of the refinery, the flash point has been reduced down to 35, because India is basically a diesel-driven economy, and we consume almost close to 72, 75 million tons per annum of diesel. So every refinery tries to maximize diesel production. The fuel oil, basically, which is actually in many refineries, it is the long residue or atmospheric residue which actually goes to make the fuel oil. The sulfur content, the sulfur specification used to be 3.4 to 4.5%. In the last 1 year, actually, there has been an intensive debate, and slowly the sulfur content has actually been reduced down to 1% of the fuel oil in order to actually put less of sulfur dioxide into the atmosphere. The flash point, of course, is a very important criteria so that we don't actually we have safety in handling fuel oil, and it comes in several grades depending upon the viscosity. So these are the four grades of fuel oil. This is the light fuel oil, medium fuel oil, heavy fuel oil, and extra heavy fuel oil, which is actually depending upon the viscosity. And each industry has its own requirement depending upon the design of the furnace. Now, coming on to the type of column internals that you see, there is nothing really new to discuss here other than what you already know from your undergraduate classes. But actually, not very long ago, the trays that were installed both in the main crude column as well as in the naphtha stabilizer were bubble cap trays. And the bubble cap trays picture you already have seen. It is actually a riser on which a cap is fitted with slots on the sides so that the vapor, when it comes up from the bottom, it actually gets diverted to these slots. And you have liquid, I mean, this entire chimney, this bubble cap is actually submerged in liquid. So the vapors actually bubble through the liquid pool, and that is how you actually do liquid vapor contacting. So the bubble cap is a pretty efficient device. The only problem is in bubble cap trays is that the delta P is high. That means the pressure drop per tray is pretty high. Generally, the thumb rule is that we don't actually allow more than 3 millimeter mercury pressure drop across each tray. But lesser the pressure drop, the more efficient your distillation will be. Because see, what happens is that in a distillation column, whatever may be the distillation column, you have only a control on the top. That means you can control the top pressure. So if you come to the naphtha stabilizer here, I can actually control the top pressure here by actually taking out this non-condensables and putting a control valve. So you have actually already studied, I'm sure, in your process control as well as in mass transfer, you must have studied how pressures are controlled in the distillation column. We don't have time to actually get into the process control side of things. During some extra time, if you have any questions, I will be very happy to answer them. But you actually put a pressure transmitter here on this line and then control the pressure on this column by actually operating the valve, which is the non-condensables going out. So you control the top pressure. The bottom pressure is actually dependent on the top pressure plus the pressure drop across these trays. So if suppose you have 50 trays and if you have 3 millimeter pressure drop across the tray, and then you have 450 millimeter mercury pressure drop, which is roughly about zero point 0.5, 0.6 kg. So if the top pressure is 11, the bottom pressure could be something like 11.6 or 12 kg. So what happens is that, as you already know, in your undergraduate classes, we try to minimize pressure in distillation column because the lower the pressure, the better is the relative volatility. If you remember that from your Raoult's law. So so here again, so coming on to the type of internals, so the bubble cap is a good device. It actually is a very good vapor liquid contacting device, but it has a higher delta P. So people came up with another design. This is a valve tray. What is the valve tray? Actually, you have a plate, the tray, on which there are perforations through which actually the vapor comes up. But these perforations are covered by a cap. So the perforation is covered by cap, which is actually lifted. So these caps have 2, 3 legs actually below that. So basically, when it gets lifted, it doesn't come out. The legs actually do not prevent it to come out. They're actually twisted below. So the legs are twisted below the tray. And so depending upon what is the vapor velocity, it actually might get raised higher or lesser. So that actually creates the aperture through which the vapor actually goes sideways and then bubbles through the liquid on the tray. So it actually creates a flow area. These are actually very, very common and very popular trays. In fact, most of the distillation columns that you will see would have actually valve trays. This is called a, why it is called valve? Because if the vapor velocity is less from the bottom, then it closes, it actually closes down. And if the vapor velocity is high, it opens up. So basically, it helps you to control the vapor liquid contacting depending upon the vapor flow. So which is pretty neat and pretty nice. On the other hand, the simplest type of configuration is what you can think of. This is actually the downcomer, and this is the sieve tray, and this has got just perforations. So basically, you provide a weir on the column on the tray. So above so the liquid actually flows over the weir. It actually creates a layer above the tray through which actually the vapors bubble, and the vapors come through these sieve holes. And so the number of holes, etc. So that is all designed, and I think you must have studied in your undergraduate classes in terms of the hole velocities and the arrangement that is done. Now coming on to the product zones, actually this just summarizes what we have discussed so far. A number of roughly about 50 trays are provided in the crude column. The crude column is roughly about 45 to 50 meters tall, and the bottom stripping section has 4 to 6 trays. The fly zone 4 to 6 trays, etc., etc. Roughly between each section, you have distribution like that, and pump around is basically the heat transfer zone. So we have 2 to 3 trays there. And this table gives you the typical efficiencies. I think this table is something for which is very good, and it will be very important for you to refer to in your future career as well, because these numbers are pretty good thumb rule numbers if you're doing a initial design of these columns. So these are the various kinds of columns that we use in refineries. A general principle is that if you're actually fractionating components which are very close boiling, like for example, if you're separating propylene from propane, where the relative volatility is only 1.04, 1.05, those kinds of columns, the trays give you pretty high efficiency. Like for example, de-isobutanizer. De-isobutanizer is actually separating isobutane from normal butane. The difference in the boiling point is not very high. So the lesser the difference in the boiling point, or the lesser the relative volatility, the more is the tray efficiency, and that actually is given by O'Connell chart. O'Connell chart is tray efficiency on the y-axis, and on the x-axis you have relative volatility into viscosity. So you would have been taught this O'Connell chart in your undergraduate classes. But coming on to the crude column, these are the tray efficiency that you see. Again, as I mentioned last time, as you go up from the bottom to the top of the column, the tray efficiencies do improve, because at the bottom you're actually trying to fractionate streams which are relatively large in terms of relative volatility, but as you go to the top, the relative volatility reduces. So this is a good, data to keep to be able to refer to later. Now coming to the second column that we have in this setup called the vacuum distillation unit. Again, that picture which I showed you earlier. So the atmospheric residue, which is whatever liquid we could not distill at atmospheric pressure. And if you recall, we cannot go above 360 degrees Celsius, because above 360, this cracks. So what do we do? In depending upon the crude, the long residue or RCO can be as high as 60%. Okay, so we need to actually recover the heavy fraction from there, so that we can use it. We can figure out what to do with that in order to make useful products, and that is actually done in vacuum distillation column. Vacuum distillation column, the name is derived from the fact that this column is operating under vacuum, and it is pretty high vacuum. It is pretty high vacuum. Actually, there are these vacuum distillation columns, we have three types of vacuum distillation units in the industry. One is actually which is completely dry vacuum. In other words, and there is no steam which is put at the bottom of the column. So this is just 10 to 15 millimeter mercury, and this is the absolute. So you can see that it is very deep vacuum. So atmospheric pressure is 760 millimeter mercury. 760 minus 10, so 750 millimeter mercury vacuum is created. So it's a pretty high vacuum. So the one type of vacuum is where there is just dry vacuum, no steam. I'll explain that later. On the other hand, you have on the other end of the scale, you have a steam at the bottom, and because steam actually creates pressure in the vessel, in the column. So basically, these columns are operated at slightly high pressure, 70 to 80 millimeter Hg. Absolute. And then somewhere in between is damp, where we don't put that much amount of steam, low steam, and so the pressure of these columns is somewhere between 10 and 70. How do we actually generate such a high vacuum? In fact, in our industry, we have actually invented a device called steam jet ejector. I think you must have studied that in your undergraduate classes. It is actually using the principles of Bernoulli's theorem to be able to actually, transfer kinetic velocity to a pressure head. And I'll explain later how. So if you recall your Bernoulli's theorem, there's a relationship between delta P and velocity. So it works on that principle. And also you could have a vacuum pump, which actually sucks the vapors out from a low pressure to a atmospheric pressure. There are actually two types of distillations that we do, or two types of fractionations that we do in the vacuum distillation column. 90% of the vacuum distillation columns are the types that you see on the left, where actually what we try to do is to distill off whatever we can do below 360 degree. So again, the vacuum distillation unit, the bottom temperature actually is 360 degree at that particular pressure, at that particular vacuum. And whatever gets distilled off is actually we get three products there. Some amount of diesel we get. It is actually called vacuum distillation, vacuum diesel, because this is the diesel fraction coming out of the vacuum tower. And why do we get this diesel? The reason we get this diesel is that sometimes some diesel fractions, the heavy diesel fractions, they don't get separated because of poor fractionation in the atmospheric column. So they come to along with the long residue. And so we actually catch them here in the vacuum tower. So this is the first product which is withdrawn from the top. Okay, and then we have what is called as a light vacuum gas oil and the heavy vacuum gas oil. And so this is the second fraction, and this is the third fraction. And then, of course, similar to the atmospheric column, here also we actually try to heat up slightly more so that we actually get a small amount of slop oil, which is a wash oil, to actually wash the fraction between HVGO and now what we call as a short residue or vacuum residue. So this is actually more or less these types of columns. What they do is that they produce these feedstocks which are cracked further in what we call as a secondary processing units called fluidized catalytic cracking unit or hydrocracker. So you can see here the light vacuum gas oil and the heavy vacuum gas oil. In this case, the heavy vacuum gas oil goes into a hydrocracker. The hydrocracker, what it does is that these large molecules that you have going all the way from C25 to something like C50, that is carbon range 25 to carbon range 50, that is actually cracked. Those larger molecules are cracked in the presence of hydrogen at very high pressure. To produce all the useful products that you and I use, like gasoline, diesel, kerosene, etc., etc. Or actually, it can go into a fluidized catalytic cracking unit. It is called FCC unit, where you actually crack in the presence of a catalyst, no hydrogen here, and you get olefins, you get naphtha, and you get diesel. So these are two very important secondary processing units in a refinery. In this course, I will teach both of these units to you. In fact, they either FCC or a hydrocracker or both are actually a part of every refinery in the world. Because this vacuum gas oil, we cannot leave it go just like that. The only thing is that if suppose the crude doesn't have too much of long residue, like in case of our Assam crude, and like in some of our northeastern refineries, we don't have a vacuum distillation tower because, like in Guwahati refinery of Indian Oil, because we don't have much of long residue, and that long residue is sent directly to the delayed coker there. So as of now, just remember that these vacuum gas oils, light vacuum gas oil and heavy vacuum gas oil, they are actually feed to the downstream secondary processing units called the fluidized catalytic cracking unit or the hydrocracker. On the other hand, 10% of the vacuum distillation units are actually they produce lube oil, and this lube oil is you and I use in our vehicle. So if you remember the motor oil that actually if you take your car for servicing, they actually put an oil. It is called as a crankcase oil, and you use a dipstick to actually see the level and the quality of that oil. So that oil is what is actually being produced by this vacuum distillation unit. And this oil, actually the oil we use is actually a blend of several oils, which is spindle oil, light neutral, intermediate neutral, heavy neutral. And these are actually depending upon the viscosity. So spindle oil is the lowest viscosity, light neutral is slightly higher. This is also called IN, intermediate neutral, and then heavy neutral. And then, of course, you have the vacuum residue, same as here. And these oils actually are not directly used in the vehicle. They contain significant quantity of paraffin wax, and they contain significant quantity of polynuclear aromatics. So they are removed. Wax and aromatics are removed, and the rest of the oil actually is the oil that we use in our vehicle. So and this cannot be produced by every crude oil. Okay, so you need lube bearing crudes. Crudes which contain significant quantity of naphthenes and alkyl benzenes. They are the crudes that are required to make lube oil in a refinery. In our country, there are three refineries which are actually producing lube oil based on the vacuum distillation unit which is producing these streams. IFC Indian Oil Corporation refinery in Haldia at Haldia in West Bengal, which is very close to Calcutta. Then we have CPCL, this is Chennai Petroleum Corporation Limited in Manali, which is on the outer suburb of Chennai. And here in Mumbai itself, in Chembur, you have Hindustan Petroleum Corporation Limited, HPCL. So they also make lube oil. So we have three lube refineries in our country, one on the west, one on the east, and one on the south. Bharat Petroleum also makes lube oil, but that is based on a different technology. But these are actually what we call as straight run lube oils. Uh, these are the typical specifications on these light vacuum and the heavy vacuum gas oil products. Basically, the specification, friends, are driven by what kind of impurity level that you can tolerate in the downstream process. So if suppose this goes as a feed to the hydrocracker, then we don't allow ASTM endpoint greater than 565. So because otherwise you'll have significant quantity of asphaltenes and metals coming along. And so we try to limit the metal content and the condenser carbon residue and the asphaltene content so that we don't actually affect the catalyst which is used in the hydrocracker. Otherwise, the metals will go and get deposited on the catalyst, and the catalyst will get deteriorated. But in order to protect the catalyst, what we also do is we have a hydro demetallization section separately. So actually, the metals get separated upfront before actually the material goes down. So this is what we try to do. And when you talk about the FCC unit, in FCC, actually the specifications are a bit relaxed as compared to hydrocracker. Here, actually, the metal factor is slightly higher. That is the nickel and vanadium. And the 10 times nickel plus vanadium is called the metal factor. And vanadium is a big poison for the FCC catalyst, and we'll get into very great detail when we talk about FCC in this class. And the conversion carbon residue. So basically, CCR is actually a function of asphaltenes, as you already know. So basically, the design and the operation of the vacuum distillation unit on the left is primarily governed by the specification of the feed in the FCC unit and the hydrocracker, depending upon which unit do you have. But on the other hand, if suppose we have the vacuum distillation unit, which is like the one on the right, which is producing lube oils, then we actually design the column in order to meet these following specifications. This gas oil is just the diesel component coming back from the atmospheric residue. But the spindle oil is a pretty light lube oil. You can see the viscosity 3.5 to 3.6 at 98.9. You must be wondering why this funny number of 98.9 degrees Celsius. Actually, if you work out the maths, then this 98.9 corresponds to 210 degrees Fahrenheit. And I mean, my apologies, because most of the industry is driven by FPS units here, because that is the units used by the US even today. So at viscosity in centistokes, this is values in centistokes at 210 degrees Fahrenheit. So spindle oil is a pretty light oil. There are a lot of see, actually, these lube oils are not only used in the vehicles but also in the industry. And roughly it is a 60-40 ratio. So 40% of the lube oil that is produced, and we produce in India close to around 4 million tons per annum of lube oil in all the 4 refineries put together. So 4 million ton of lube oil finds its way into 40% of that actually finds its way into our automotive industry. But 60% is used in the industry, in the machines. So these are called industrial oils. So in your pump or in your compressors and stuff like that. So there are a lot of rotating machineries which use lubricating oil, and this is the light oil which are used in some machines. Then comes the light neutral, and the intermediate neutral, and heavy neutral. In fact, the intermediate neutral is the most important and the precious lube oil, 9 to 11 centistokes at 210 degrees Fahrenheit, light neutral and heavy neutral being on the either side, and of course short residue. And of course, one thing that you need to remember is that the lube columns are typically wet vacuum, as products need to meet flash point specifications, because like in our crude distillation column, kerosene, diesel, etc., had to meet the flash point specification. Same thing here as well. Okay, now coming to how these crude columns look like, this is actually the way the crude column, the vacuum towers are designed. So you got atmospheric residue, and it is very similar to the crude distillation column, atmospheric distillation column that you have studied. So the atmospheric residue coming from the atmospheric distillation unit is put into a furnace, and we get preheated it again. So it is coming at 360 roughly, and we preheated it to 415, etc. So in order to vaporize all the vacuum gas oils. And remember, this column is operating at 10 millimeter mercury absolute at the top. This is actually dry vacuum distillation unit. As you can see, there is no steam stripping here at the bottom. And one thing that you would have noticed immediately, I hope, as compared to atmospheric distillation unit, there are no strippers here because these are not end products. This is not the end product that you and I will use. So there is no safety in terms of handling. So there is no issue in terms of safety and handling. So these products are withdrawn and actually put straight into either fluidized catalytic cracking unit or the hydrocracker. So the furnace, it actually here this is the fly zone as before, where the now in this case the short residue or the vacuum residue drops out to the bottom, and then you have vapor going to the top. Now this is actually the wash section where we don't allow any short residue droplets to actually go along with the vapor. Because if they go, then it will carry significant quantity of asphaltenes and metals, and that will affect the quality of the first withdrawal, that is the HVGO. So here we actually, as the vapors go up, same idea. That means we withdraw the liquid, and of course this withdrawal, I've not shown a pump here, but and from high vacuum to atmospheric, you cannot withdraw unless you have a pump, right? So this liquid, which when it gets withdrawn from the column, there's a pump, and the discharge from the pump is actually goes into three different directions. One part actually goes as a reflux to the column itself. So actually the vapors, when they come up, they get washed by this liquid. And in vacuum distillation units, we actually don't provide trays. In old days, actually there was there. I mean, most of the old vacuum distillation columns, which old means designed before 1970, they were provided with trays. But then over a period of time, they got replaced by random packing, and now what we call as a structured packing. And I'll come back to that later as to what is a structured packing. And that part of that liquid is withdrawn as a product, which we call HVGO, and part of it is cooled and then put around as a pump around. Same. So that what does this pump around do? It actually condenses all the HVGO components rising in the vapor, present in the vapor rising to the top. And then the same thing happens here. The vapors going here contain LVGO. So that LVGO part is actually condensed, and you can see there is no overhead condenser here. So this pump around does the job of the overhead condenser. So it tries to condense everything possible, and whatever is not condensed is actually basically uncondensable gases. These are called non-condensables. Just remember that this top product which is going is not exactly a product. It is just a stream which contains non-condensable gases like dissolved oxygen, dissolved nitrogen, or actually gases which get formed due to cracking in the furnace. Because now we are going up to 415 degrees Celsius, so there will be some cracking of the hydrocarbon. So that cracked gases, which are basically C1, C2, C3, C4, they come to the top. And these is what we call as steam jet ejectors. So you can see that here we are using three-stage steam jet ejector. This is the first stage, this is the second stage, and this is the third stage. How do they work? We have a very high pressure steam, high pressure, not very high pressure, but this is high pressure steam. And this is actually put through a converging diverging nozzle. So you can see that this is the converging and this is the diverging nozzle here. And when actually this goes through a converging diverging nozzle, according to Bernoulli's theorem, it actually creates a vacuum. I mean, it creates a kind of a vacuum here, which actually sucks this vapor. And then actually it comes out, and whatever can be condensed, so the steam gets condensed. And then the steam and whatever hydrocarbon might be coming through gets condensed and goes into this drum. And basically, the height of the length of this pipe is what is called as a barometric leg, which is 10 meters minimum, minimum 10 meters height, because 10-meter water column is equal to 1 kg per square centimeter. You can work out this calculation that if you actually have a pipe of length 10 meters, then if the pipe top is exposed to atmospheric pressure, then the bottom of the pipe would have 1 kg per square centimeter pressure. And that you can, that is H rho G by GC, so height into density. And so if suppose we have full vacuum here, so very high vacuum, so you need at least 10 meters height before you actually can be assured that the bottom of the pipe is equal to atmospheric pressure. So that is what this overhead drum is. This is actually at atmospheric pressure. And all the non-condensables which we could not condense even in this goes out from the top, and the hydrocarbon is separated as a separate layer here, and the process water. This again is sour water because there might be H2S dissolved here. In what when we talk about a three-stage what you call a steam jet ejector, so what happens here is that it will create some vacuum, and this is the highest vacuum, and then the next is the slightly lower vacuum and the lower vacuum. So this is almost this is, let's say, 10 mmHg, and this could be 30, this could be 80. So whatever cannot get condensed, they actually get sucked into the second stage steam jet ejector, and similarly here it gets sucked into the third stage steam jet ejector. These are steam jet ejectors in series, and you got power steam coming in all of them in parallel. So it actually sucks in the vapor here and condenses the steam. So it actually creates a vacuum, and then whatever could not be condensed, it actually takes into the second stage and the third stage. So these are like very neat. These can be very large capacity steam jet ejectors. The biggest advantage for us in the industry is that there is no moving parts. If you put a pump, there's a moving part, there's a maintenance, and all kinds of issues. But here, actually, these steam jet ejectors, they run silently and create the vacuum that we need. So this is a very important part of a vacuum distillation unit. On the other end, if you have a wet vacuum, so what we do is that we put stripping steam at the bottom, and some part of the steam is actually put here in the furnace banks, actually in the tube banks in the furnaces in the furnace, so that actually we can go slightly higher on temperature, but still don't do any cracking, and because it is, I mean, the partial pressure of hydrocarbons is lowered since we have steam. The overhead, the configuration at the top is the same. So you got vapors coming in, and then actually you got the washing going on here, and the same three streams going out, and the LVGO, same, exactly the same configuration. Now, in many cases, actually, these two vacuum gas oil streams, the light vacuum gas oil and the heavy vacuum gas oil, they are actually combined together to actually send it to an FCC unit. So the LVGO and HVGO, they are combined together to form vacuum gas oil and put together to an FCC unit. So you might ask me that why the hell did we separate out LVGO from HVGO if we have to mix the two again? The reason is that actually there are three good reasons why we actually, and please remember that, why we actually separate out the LVGO and HVGO separately. There are three good reasons for that, and all the three reasons are linked with the economics of this vacuum tower. So remember, this vacuum tower is at a very high vacuum, and because of that, the vapor flow, velocities are high. So in order to actually have reasonable vapor velocities, we actually have a pretty large diameter of these vacuum towers. Some of these vacuum towers can be as high as 20-meter diameter, 20-meter diameter. And as a result, actually, what we try to do is to control the vapor liquid traffic in this column. So actually, by taking part of this liquid cooling and condensing, we reduce the vapor going to the top. So because we are withdrawing the HVGO. And similarly, the liquid that is coming from suppose if I don't have this LVGO, HVGO withdrawal, and we withdraw everything from the top, then actually the entire vapor liquid traffic will be very high. So that is why that is one economics that we can have good control on the column diameter. Number two, of course, since we actually can withdraw at a higher temperature, so this is a very useful heat to be used in the crude preheat train to preheat the crude. So higher the temperature, the more useful heat it is. So in fact, these HVGO pump arounds can be used in the hot preheat train. Thereby, we actually increase the preheat temperature before it goes into the furnace. And LVGO is of course lower temperature. Generally, this actually lands up in the warm preheat train. So this is another reason why we actually fractionate the LVGO and HVGO separately. And the third reason is that if suppose the refinery has a hydrocracker, they try to maximize the LVGO going to the hydrocracker because this is a pretty neat material. It has less metals, it has less condensate carbon, it has less asphaltenes. So it is a pretty good material to be taken into hydrocracker with a little bit of HVGO. So separating LVGO HVGO provides a great flexibility to the refiner, depending upon his downstream units, to be able to mix different ratios of LVGO and HVGO while it is being processed in the secondary processing units. Here, of course, since this is a wet vacuum, you need a pre-condenser so that the steam coming here gets condensed. Otherwise, you load the steam jet ejector for no reason. So the steam coming is actually condensed, and then you have only two steam jet ejectors because here these operate at relatively high pressure. There are many design variables in this column. I think the most important we will discuss. It is actually the type of internals that you provide. Now here, when we talk about column internals in a distillation column, in a vacuum distillation column, the earlier discussion that I was doing in terms of the pressure drop in the column assumes very high importance because with great difficulty with all this paraphernalia here, we create a 10 mmHg vacuum here. And if suppose if at the bottom it is 100 mmHg absolute pressure, then there's a 90 millimeter pressure drop. Actually at the bottom the pressure is very important because this flashing, if it can be done at a lower pressure, to that extent I can do a more lift here. And that is the reason in these vacuum towers, we try to minimize the pressure drop between the top and the bottom. Generally, if suppose we have 10 millimeter Hg at the top, we try to not exceed 40 to 50 millimeter Hg at the bottom, roughly about 30 millimeter mercury pressure drop across the column. And that is why actually, we have come up with the concept called structured packing. I'll come back to that in a moment. This is just to give you what is the heater outlet temperatures here. They're slightly higher, but basically we put it along with the steam. And the fly zone temperature depend upon the feed inlet temperature, but also to take into account the overflash or the wash oil. These are the different pressures that we operate. As I already told you, dry vacuum is pretty high vacuum. Wet is on the other hand relatively high, 75, and damp is somewhere in between. Damp actually, your steam flow rate is somewhere in between 0 and something like 18 to 20 kg per meter cube that we had studied earlier. As far as the column diameter is concerned, it is highest here because it's pretty high vacuum. So the vapor velocities become very high. Just imagine, just apply your ideal gas law, PV is equal to nRT. So pressure, volume is inversely proportional to pressure. So the volumetric flow rate in terms of meter cube per hour goes up when your pressure goes down for the same number of moles. If your volumetric flow rate goes up in terms of actual meter cube per hour. And in order to handle that large volume, you need a larger diameter to keep reasonable superficial velocities. But if you go up even 10 times the pressure, 8 to 10, you drop the vapor velocities by 10 times. Of course, you have steam. So the column diameter is least here and somewhere in between these two here. So this is just to give you some idea and operating parameters in these three types of columns. I think I'll skip this slide, but what is important to know is what is structured packing. So this is actually it is not new, it is not new. I mean, this has been around in the industry, yeah, but relatively, uh, relatively new, I would say. I think this invention took place while I was in EIL, Engineers India Limited. I think somewhere around 84, 85, the structured packings got introduced to actually reduce the pressure drop. Why it is called structured packing? Actually, what happens is that if you take a plate, a very thin stainless steel plate, the thickness is almost zero point 0.1 millimeter. So it's almost like the edge of your knife. And then you actually twist it. So you provide these kind of twisting on the tray, and then punch holes. So you actually take a thin sheet of stainless steel, and you punch holes in that. So these are the holes there, and then actually you provide these. You crimp them. You crimp the sheet. So you get these crimps like this. And these sheets are then arranged in a crisscross manner. So this is one crimp sheet, then this is a second crimp sheet, and the third crimp sheet like that. So you actually put them one behind the other, and then tie them together, okay, with a stainless steel metal wire. And depending upon the column diameter, you can actually uh, change the length of the sheet. So here the length of the sheet is less, so we actually make these sheets of different length, so that we can actually put them together to fit any column diameter. If the column diameters are very large, like 20 meters, etc., then actually it is made in sections. So what you do is you make sections like this, sections like this, and many sections are made like this, and they are put together and tied up together in the column, with, of course, support plate, etc. So you put a support plate at the bottom, and then you put all this packing one above the other. What is the advantage of that? The advantage is that, as you know, the mass transfer, in case of packed distillation columns, the mass transfer takes place on the surface of the packing. So basically, the liquid coming from the top, it wets the surface of this packing, and the vapor, when it rises from the bottom, it actually carries out the mass transfer with the liquid, which is wetting the packing. So depending upon the crimpness of this plate and the holes that you drill and the thickness of this sheet, you could actually vary the surface area. So we have structured packing, which are designed to provide all the way from 100 or even 50 square meter per meter cube of the column volume to 750 square meter per meter cube. That means if you have 1 meter cube of column volume, the surface area provided for mass transfer by these structured packings can go anywhere from 50 meter square to 750 meter square per meter cube. And the higher you go, the more will be the pressure drop, because the density of putting together these sheets will go up. And this space that you can see in between is where the vapors go up. And since there is less resistance for flow to the vapors, the delta P is low. So that is how we actually that. So these structured packings provide a very low delta P, very low pressure drop across the packing, and it actually helps us to meet our target of something like 40 to 50 millimeter mercury pressure drop in the tray. So this is a good, photograph of a structured packing. These are some data in terms of, this is very important. The top temperature, again, we don't try to reduce it below the, in case of wet vacuum, we don't try to reduce it below the acid dew point because uh, the atmospheric residue does have sulfur compounds. And in the furnace, actually, this atmospheric residue can crack slightly and you can have H2S produced. So again, we try to actually maintain the temperature slightly higher. As far as the ejector load is concerned, I mean, how do you design the steam jet ejector? For that, we need to have a fairly good idea about the amount of non-condensables which are going through. And there are engineering methods by which we calculate the non-condensables. Of course, one is the solubility of oxygen or air. If suppose we are taking this long residue from a stored tank and it is under nitrogen blanketing, then the nitrogen solubility in that, plus actually the cracking that happens, plus any leakage which can happen through the flanges. So these are very tall columns, and these tall columns are actually having flange connections, flange joints. So these flanges are normally not very airtight in the sense that we try to do it airtight, but there is some leakage which happens because there is very high vacuum inside. So there are, depending upon number of flange joints, there are formulas by which you can calculate how much amount of air must be getting in. And based on that, we actually design the ejector. And this is how actually the steam jet ejector looks like. So you got steam coming in, and then you have a converging nozzle, and then followed by that is a diverging nozzle. So this is the injected nozzle, that's the steam through which actually the steam is injected. And when it gets injected, it actually creates a thrust through this converging diverging nozzle, because of which this gases get sucked in. And then this goes into the condenser, and then you have this what you call as a barometric leg. If you're talking about compressor, this is actually a liquid ring vacuum pump. This can also go to pretty high vacuums. What we do here is that we have an impeller which moves around the liquid. Now, depending upon what vacuum you want to create, you have to use the liquid accordingly. So, if suppose you're talking about 10 millimeter mercury vacuum, then this liquid should not vaporize at 10 millimeter mercury. So, it has to have a very high boiling point. And so, it actually, when the impeller rotates, it actually takes in the gases from the tower, and then it throws out the gases here. And it not only throws out the gases, but part of the liquid as well. And so you take it out into a separator vessel, and then the liquid is sent back into this casing, and the vapor is taken out. So this is what is called as a liquid ring vacuum pump. I'll just very quickly walk you through a commercial example of a crude distillation unit. This is an actual crude distillation unit operating in a refinery. This is, as you can see, has something like 43 trays with a small packing zone here. There are two fire heaters. In fact, this is a pretty large crude unit. And so that both the vapors come here in the fly zone. And this is the stripping section from which we remove the long residue or vacuum residue, atmospheric residue, and then go through the vacuum furnace into the vacuum tower. And the first withdrawal here, as you can see, is that of the this is a very heavy gas oil which actually goes to the FCC again, the fluidized catalytic cracking unit. And then you have the second withdrawal from here. The second withdrawal is here, which is actually the diesel product, which is being withdrawn after steam stripping. And then the next withdrawal, as you can see, is the kerosene fraction. Again, 6 trays here, 6 trays here, around 10 trays here. And here you can see that there is no steam stripping. There is a stripping steam here, but there is no stripping steam here. This is actually a reboiler, because this is actually the jet fuel that we are producing there. And then, you have this top section, Where in this case, what these people have done is that they are trying to recover that heat also into the crude. So all these heat exchangers that you see here is preheating the crude. Similarly, this heat exchanger also is preheating the crude. So all these are pump arounds. So you can see that this liquid which is being withdrawn as a diesel, part of it is pumped as a pump around after cooling to the top. Okay, so this is like 31 to 34, four trays here, two or three trays in the pump around here. Similarly, this is another pump around. This is Yeah, sorry. There's another. This is the light kerosene. This is the heavy kerosene withdrawal. Again, there's a reboiler. There is no open steam stripping here. So this is, and then the overhead. Actually, you have a crude being preheated by the overhead vapor, and then a fin fan cooler, and then of course a receiver. In this case, the non-condensables are compressed and try to be. There's a further liquid being recovered here. So this is actually just to give you a complete perspective. And the same refinery has this vacuum tower also. This feed coming from the bottom is taken to the vacuum tower, and here we have the same. Only here that we actually there's a diesel also being withdrawn, and so actually you have again steam jet ejectors etc. here. And these are this is the LVGO, this is the HVGO, and vacuum residue. And this is actually the just to give you an idea. This is the cold preheat train of that refinery. So you can see that the crude comes in, gets splits into two trains. This is where heat is recovered from the overhead vapor, and this is another heat recovery. Then actually this gets split into another three trains, and it's pretty complicated in terms of and then ultimately it goes into the desalter at about 150 degrees Celsius. After desalter, from the desalter it comes, and the warm preheat train is pretty simple, and it goes at about 170 into the flash drum, the where we take out the it's pretty reasonable, pretty significant quantity, about 45 tons per hour. And then at the bottom you have the topped crude, which actually goes into what is called as a hot preheat train. This again gets splits into three trains, and there are two furnaces. So through both the furnaces, the capacities are large, so both the furnaces operate, and ultimately the outlet temperature is about 386. So this is what I had actually in terms of. So this actually finishes our our discussion on the crude and the vacuum distillation column, and basically the primary unit called the crude unit.